Okay, so
You knew about that, Albert. What? We decided you knew about Lagrange.
yeah, we thought you're excused from. So. So last time we saw, given L0, L1, Lagrangian submanifolds of our symplectic manifold M, we defined the Floer cochain group be the lambda vector space generated by transverse intersection points between L0 and L1. And we saw that if they don't intersect transversely, we can move them by a Hamiltonian symplectomorphism so that they do. So now, given a whole collection of Lagrangians, we define, and intersection points Pi in Li minus 1 intersect Li for all I mod S plus 1. Define a moduli space so this is, okay, we're going to call it that, but in practice we're going to use a pictorial notation for it, which is much easier to see what's going on, which is this. And what is the definition of this space? It is collection of S plus 1 ordered points in order around the boundary of the disk. That's the notation for the disk, together with a map from the disk minus these boundary points into our manifold, J holomorphic, mapping the component of the boundary between Z I and zeta I plus 1 to Li, asymptotic to intersection point Pi as you approach boundary puncture zeta I, modulo reparameterization. Where the group of holomorphic automorphisms of the disk is PGL2R, acting by Möbius transformations. So of course, because the equation we're imposing is a holomorphicity equation with respect to the complex structure small j on the disk, only holomorphic automorphisms are the ones that preserve, that actually act on this moduli space by reparameterization. Okay. Oh, that's a part, I mean, as in quotation marks. Maybe I should just remove them altogether. Just saying that's what we can call it.
Mark on the edge of the disk means it extends to a little neighborhood.
Not at the points we want, but yeah.
But you mean out here?
Yeah, first of all, out there.
Only the zero, yeah.
Yeah, I mean, well, I think it's automatic.
Yeah.
If it's it will be smooth up to the boundary and it will automatically extend.
Only continuous extension of all of these functions, but not anything else.
Yeah. Okay.
And then of course that's not compact.
That's right. That will be part of the story we'll talk about today. So there's a forgetful map from this moduli space. Which forgets the map U from our disk into M. And maps into what we'll call R script RS, which is ordered tuples of S plus 1 points on the boundary of the disk, modulo the action of PGL2R again. But this is just the domain and doesn't remember the J holomorphic map into our manifold. So the dimension of this RS is S minus 2, which you can remember because PGL2R acts transitively on tuples of 3 marked points on the boundary of a disk. and their stabilizer is trivial. Okay, say that quickly. Fibers of this forgetful map have dimension, this index of the homotopy class I guess since I haven't defined this for you, this is not such a meaningful statement, but this index is called the Maslov index, and it's a natural thing defined topologically. So this gives us a total dimension of this moduli space of maps. The index coming from the dimensions of fibers where you just fix the domain, plus S minus 2 coming from varying the complex structure on the domain, which is just this RS. Okay? I just want to make the point, since that wasn't present in the moduli spaces we looked at last time. Question? Yes. So right. So I'm going to talk about S equals 1 exactly now. So last time we defined this differential in the Fleur cochain group between two Lagrangians. To be the sum over all Q and all homotopy classes beta of our disks. So let me say by convention, so this beta is a homotopy class of the disk. This symbol hash means assigned count of the zero-dimensional component of the moduli space. Of this one. So just to explain why this is the same as what we said last time, any disk with two boundary marked points is biholomorphic to a strip when you remove these zeta naught, zeta 1. And the remaining automorphisms of this strip, where imagine zeta naught and zeta 1 is being put exactly opposite each other on the boundary of the disk. Are acting by translations, translations, moving in this direction like that. So in this case, S equals 1. So the zero-dimensional component should have index of beta equal to, plus S minus 2 equals 0, which means index of beta equals 1. So this agrees with what we said last time. We count strips with index such that the moduli space of such strips has dimension 1, and then we quotient by the action by translation. This was the definition we gave last time for the flow differential. We were working last time with the assumption that they're intersecting transversely. Yeah. And we had other assumptions to rule out sphere and disk bubbling. Under certain assumptions, which for last time we took a very conservative one, that the symplectic class vanishes on any disk with boundary on one of our Lagrangians. We saw that the boundary squares to 0 because boundary points of the Gromov compactification of the one-dimensional component of this moduli space are in one-to-one correspondence with well, they exactly consist of these nodal spheres, so nodal disks, sorry. Which are in one-to-one correspondence with terms in the equation for del squared of P. It's P here. And in particular, this is now a compact one-dimensional manifold, so the signed count of its boundary components is 0. So, in particular, this thing is 0. We went on to define the Floer cohomology group to be the cohomology of this differential. And we saw, again under this assumption, that symplectic class vanishes on disks with boundary and a Lagrangian. That if you take Floer cohomology of a Lagrangian with itself, that is isomorphic to the cohomology of the underlying manifold, the underlying Lagrangian. Okay. More generally, there's a spectral sequence from this to that, but under this assumption, they're just isomorphic. Yep.
There's a spectral sequence which maybe doesn't degenerate. Is that because there's some symplectically defined filtration?
Yes, the filtration is the filtration by energy on the Novikov field. So if you remember the coefficient ring we're always working on, is this Novikov field, and you define filtration like that. And then this induces a filtration on your Floer cochain groups because you're given a basis for them, so the filtration on this guy. And then what this is saying is that, yeah, what it's saying is that the energy zero holomorphic disks correspond to Morse flow lines. Bigger holomorphic disks give corrections to those.
In order to compute this HF star LL, you form L equal L prime. An exact
Yes.
deformation, so lies in the true neighbor of L, you can do it as a graph of Morse function. That's precisely equivalence.
Yes.
And then
Yeah,
that's
yeah.
precisely what you just said. And then if you look at low energy things, these are just the flow lines and higher
Yeah.
than the other.
Right. Okay. So that was just defining the underlying Floer cohomology group. But now we have extra operations on it. We have a map mu2 from Floer cochain group from L0 to L1, tensor, this is tensor over our coefficient field lambda, cochain group from L1 to L2 into cochain group from L0 to L2. And this was defined by using the same conventions as before. We defined this mu2 like that. And we saw boundary points in Gromov compactification of one-dimensional component of the moduli space are again in one-to-one correspondence with certain nodal holomorphic disks. And this one corresponds to this one is that, and using the same thing that we will just keep using over and over again, the signed count of boundary points of a compact one-dimensional manifold is 0. That means that the sum of these terms down the bottom is 0. I'm going to put plus minuses for the moment, but I'll explain, well, I already explained what sign conventions are going to be in some sense, but we'll make it precise later. So from this equation, it's some sort of Leibniz equation. So it implies that this mu2 descends to cohomology. Okay. Now we want to know if this multiplication kind of map mu2 is associative. Well, we define okay. I'm going to going to define a new operation. It's going to be a map that looks like that, and it's going to be defined by this formula. Now, what algebraic relationship does this one bear to the ones we've looked at previously? Once again, we look at so I should really have some kind of LaTeX macro for doing this on the blackboard, but it's we want to look at the boundary components of the Gromov compactification of the one-dimensional component of this moduli space, where here we were counting the zero-dimensional component of the same moduli space to define this mu3. And they are that one that one and that one. Okay, so what is this telling us algebraically about if so once again the signed count of these guys must be 0 since they're the boundary points of a compact one-dimensional manifold. So this one looks like a mu2. This one's a mu2. Here's one of these mu3s. Here's a differential. mu3, differential mu3 differential, mu3 differential. So put them all together, and it's telling you that mu2 is associated. First one I had was, yep. Oh, have I missed one? Oh, no? Sorry. Oh, I'm sorry, I started calling these mu1s. Okay, and this whole equation, if you look at all these terms involving mu3, of course, if P is closed, then these ones all vanish, and this one, of course, is closed itself, so this one doesn't matter for cohomology. What it's saying is exactly that mu2 is associative on the level of cohomology. Okay. Any questions about?
Explain this last one, but there's Gromov compactification in your moduli space, because it can't be a manifold if you have multiple. What's a one-dimensional manifold with boundaries like this?
Like an interval.
So could you have sort of two intervals crossing each other with the singularity, or are they really
Generically, no.
so isolated intervals?
Yes.
And but okay, so each of these is corresponding to some kind of moduli space.
Exactly. You have some moduli space, and so you you start off wanting to prove that these guys add up to 0, and you glue them into some moduli space as the ends of some one-dimensional thing, and then the ends all either connect these guys up or connect them up to some other terms in here. So the sum of all those terms is 0.
Generically, before compactification, you just have a manifold. It's not a singular.
That's right. But before compactification, generically you just have a non-compact manifold. Whereas, so that, I mean, we're always using the one-dimensional component to get the algebraic relation between things. We're using the zero-dimensional component to define the operations. So these ones are just generically zero-dimensional compact manifolds. So those ones are just ones we can count.
Dependent on those transversality assumptions.
Yes. But in this assumption makes that pretty safe. It's
And restricts the applicability.
yes. It's certainly this is. I mean, we will certainly want to break this, but it's the easiest one where everything that I say in the definition is not a lie, and then later I'll say, and it continues to work in such and such and such and such circumstances. Okay. Okay, so we've got this associative product on the level of cohomology. We saw that the Floer cohomology group from L to itself is cohomology of L, which means, and let me just say, one can show where that we have identity morphisms which correspond to the identity in degree 0 cohomology of our Lagrangian. So these act like identity morphisms for this product defined on Floer cohomology groups. All of which amounts to saying that we have a category. Maybe I should say corresponds to. So okay, I'm sorry, I wasn't very clear. EL is an element of degree 0 Floer cohomology from L to L. And which component is it? Well, Floer cohomology from L to L is isomorphic to cohomology of L, and we take the element in here that corresponds to the identity for cohomology. So yes, there is, because we can use a very natural way to realize this is via Morse cohomology, and if you choose, for example, your Morse function to have a unique minimum, then there's just one thing that the identity could be on the cochain level. But talking about identities on the cochain level turns into a bit of a complicated story in the Fukaya category. Okay. So what we've just defined is called the Donaldson-Fukaya category. Okay, so objects are Lagrangian submanifolds of M, and to not be lying, I should say with pin structure, which remember was what I claimed we needed to orient moduli spaces so that we really have signed counts of boundary points and points in moduli spaces. Grading, if we want the gradings to work out the way I'm going to claim they do, but again, I'm not going to say much about this. And we want some assumption like this to avoid nasty things involving disk and sphere bubbling.
Is there about two version where you can do that?
Yes. We just change the coefficient. No, I erased it. Just change the definition of the Novikov field so that you're looking at power something like power series, but with Z mod 2 coefficients, and that works just fine. Right. When we go to a more complicated, in this setting it's fine, but for more complicated, for more technical versions of Flow theory, one has orbifolds rather than manifolds, so one needs to be able to divide by integers in the coefficient ring. So these Flow cohomology groups are the morphism spaces in our category. They're Z or Z mod 2n graded lambda vector spaces, where lambda is this Novikov field. The composition maps in our category are yes.
But that doesn't work if I work with code chains.
No, in cochains it's more technical. Well, one has to make a choice how one deals with that on the level of cochains. Yeah. Is it
actually resolved?
Yeah, I mean, so at least in the setting that is done, for example, in Paul Seidel's book, of where some simplifying assumption like this is made, one simply takes for each pair of Lagrangians a choice of Hamiltonian that the flow makes one transverse to the other, and then one has to alter which J holomorphic curve equation one uses, but it somehow interpolates between all these extra choices. And then at the end, one has to show that what you get is independent of all the choices you made. But yes, that's done. Okay.
But you said under some assumptions. Or that was so, but in principle it should be possible.
Right. I mean, that's for exact symplectic manifolds. Right. I think for monotone symplectic manifolds, it should also be just as straightforward. Right? I mean, it is. And then one starts to get in. I mean, then there aren't even complete definitions of what the Fukaya category is for, you know, arbitrary symplectic manifolds, even claimed using whatever stuff you like. So I can't comment beyond exact and monotone. Okay. So these mu2s are the composition maps in our category, compositions of these morphism spaces. So note that I'm kind of using the opposite ordering convention from usual composition of morphisms in categories, but that's really makes it much easier to see how the moduli spaces relate to the composition operations. And the final piece of data we need is the identity morphisms. Are these ones that correspond to the identity in cohomology of the underlying Lagrangian? Okay. But, okay, so this is a perfectly well-defined category, and it's very, very interesting to study and use, but it doesn't have enough information for our purposes in studying mirror symmetry. There's a more refined version of it. And that is the Fukaya category.
So historically, was it first Donaldson?
I believe that Donaldson introduced this product and observed it was associative, as I understand it. Right, and Fukaya made the observation that this is part of this more refined structure, which I guess was interesting from when one wants to look at things like the Atiyah-Fleur conjecture, that for those also one sort of needs these A infinity structures as well. Okay. So this is what's called an A infinity category. So let me tell you what that is. As few words as possible. So a K-linear pre-category, my terminology, it's not very important. Consists of a set of objects for any pair of objects a possibly graded K vector space. And that's it. That's a pre-category. It's everything before we've introduced the structure of composition maps. We're going to introduce some notation Sorry? Yes, that's the space, the K vector space. So to save me writing out the same thing many, many times, I'm going to say, given this pre-category C, some set tuple of objects, define C of x0 through xs to be just the chain of morphism spaces from x0 to x1, x1 to x2, all the way through to xx minus 1 to xs. Now we're going to define an analog of the Hochschild cochain complex, which we already introduced for a vector space, and the definition is completely analogous. I mean, in the same way that, algebra is to category in the same way as A infinity algebra is to A infinity category. It's nothing more complicated, just you can have several objects. Let me introduce the various graded pieces. Okay, that's the definition of one part of the Hochschild cochain complex. And then when we put all these together by taking the direct product over all possible values of S, we get the full Hochschild cochain complex. Okay, and if C has only a single object and a single morphism space, this coincides with the definition that I gave earlier.
So that in the definition of the Hochschild thing is a hom over K?
Yes. Maybe I should use a... Right. Everything is K-linear. These are all K-linear tensor products and so on. Okay. So we define the Gersten-Haber product and bracket by exactly the same formulae as we used previously. Which was Gersten-Haber product was denoted by this open circle, and it was the sum with some signs of phi of blah blah blah, all ways of putting psi inside phi and inserting these inputs inside it. The Gersten-Haber bracket was some commutator with respect to this Gersten-Haber product. Okay. So if we wanted the definition of a k-linear category, by analogy with the definition of a k-algebra, it's given by a choice of mu2 in CC2 of our category C. This is called length 2, which means we have mu2 from C of x0, x1, x2 to C of x0, x2, satisfying mu2 Gersten-Haber product with mu2 equals 0, which we saw in the case of algebras is exactly equivalent to associativity of this product. Whereas a non-unital k-linear A-infinity category is given by a choice of mu in CC2 of C, where we no longer require that it be strictly in the part S equals 2, which has only 2 inputs. It looks like a usual product. But we do require that it have length at least 1 to avoid having what is called a curved A-infinity category, which we talked about when we talked about A-infinity algebras. And its Gersten-Haber product of mu with itself should be equal to 0. So i.e. mu1 maps from a Hom space to itself, degree 1. We have mu2. Has degree 0. We have mu s of all lengths s of degree 2 minus s. Okay. So those that's what mu is made up of. Those are its constituents. And these constituents should satisfy the A infinity relations. Which star? Here? This? That denotes the grading. Like, yeah, I could write it as I to I plus 1. i.e., well, what I'm saying is mu is an element of this group, or this vector space, which is a direct product of all s of these things. And so I'm saying it consists of 1 in each value of s. Okay. So i.e., mu consists of all of these components.
Is that in Paul's book?
Yes. Maybe it's a slight paraphrasing or something, but it's essentially the same. And these mu should satisfy the A infinity relations etc., which we've seen a couple of times now. So so the first observation is if we've got a k-linear A infinity category C consisting of this data, we can define a k-linear category the cohomology of C with Hom spaces in this cohomology category being the cohomology of Hom spaces in C with respect to mu1. which is a differential by that first equation up there. And composition given by mu2, which by the second of the A infinity relations descends to cohomology, and by the third of the A infinity relations is associative.
And it's the same objects.
Same objects, yes. Sorry. Okay.
So these are the associated Donaldson family.
Right. So we can now define the Fukaya category, which is an A infinity category whose cohomological category is the Donaldson-Fukaya category. So the Fukaya category has the same objects as the Donaldson-Fukaya category. Okay, I'll use DF for that for the moment. Yes. Yes. Lagrangian submanifolds L sitting inside our M with the same decorations that I mentioned in the definition of the Donaldson-Fukaya category. Okay. One can deal with that issue but I haven't done any of the groundwork to write exactly what one does. Let me say it as if that's not an issue, and then let me, in the last little bit, explain.
Before, that
Yes.
was the semicolon, but
Yes.
So he fixes some additional structure in this, and so that actually in some coherent way the things are better against each other. So it's not just the Lagrange, but together with some deformation.
Yeah.
So in some sense, I think when you define the pre-category, it's associated to two objects. So you can presumably in this Hom notation incorporate already that the things are being actually perturbed and
Yes.
brought into a position to each other.
That's right.
I guess just to get a correct statement, we could say take a countable set of Lagrangian submanifolds such that it is
But you always need to define Hom from L to itself. So, yeah.
Oh, that line is really hard in that.
Okay. Okay, so the Fukaya category has the same objects as the Donaldson-Fukaya category, just Lagrangian submanifolds. Hom spaces.
I have a question, so just for curiosity. So when I look at, for example, a map from a finite dimension manifold where for each point I associate a Lagrange, so I'm looking at the whole family of Lagranges, and I want to associate some, I mean, that could have some interesting data. Yeah? So if I say intersected with another such family, then generically, for almost all values, I have a nice intersection, and then maybe I disregard something. So I could imagine there are some invariants. Can one do that in the Fukaya category, or is that not? I mean, you told me at some point that the Fukaya Fukaya category doesn't get all the things which one should have because of, for example, this student of Oru has sort of this new Lagrange which you wouldn't find from this structure.
Well, you wouldn't be able to distinguish it from other Lagrangians using the most naive version of flow cohomology. I believe it's expected that yes, if you have some family of Lagrangians parameterized by some space, in some sense one should be able to define some kind of flow cohomology for those. But for example, Muhammad Abu Zaid's talk was kind of about this, right? There's these family of Lagrangian torus fibers, and one saw that just to treat this, even just a family of tori, even just varying over a small interval, there are a lot of technicalities to check that one has convergent. So in those cases, the Novikov field is not enough to get the kind of convergence that you need.
It's also a question of finding the right level of generality to pose it, I think. A lot of the methods
Yes.
are just too close to the ad hoc business yet. So maybe the methods have been designed to do this. And I think maybe, then of course, one could ask that question then on a homological level or on the cochain level, which of course would be the more interesting one, but then that would be even more complicated, I guess. Because it would not just do it for two objects, but you have to do it for insufficient generality for a family of objects.
Yeah, it's.
So but I think that's presuming quite open in general.
I think so. Yes, I think there are, as expectations, some kind of family version of Lagrangian flow cohomology should exist, but it's pretty wide open what it should look like. Okay, so let me finish with the definition of the Fukaya category. So Hom spaces in the Fukaya category are now Fleur cochain groups, not the cohomology groups as they were in the Donaldson-Fukaya category. And these A infinity structure maps, mu S, are defined by counting J holomorphic disks with an arbitrary number of, with S plus 1 boundary punctures, S plus 1 boundary components constrained to lie on the associated Lagrangians. And as before, we weight by the symplectic area of this disk and multiply, and this is the coefficient of P naught in the output of mu S. The fact that this does satisfy the A infinity relations follows because terms in mu circle mu of S inputs are in one-to-one correspondence with nodal disks looking like this. P0 down the bottom, P1, etc., Pi, Pi plus 1, etc., Pj, Pj plus 1, Ps. And these guys are the boundary points of the Gromov compactification of the one-dimensional component of this moduli space. Okay. So if you look at the one-dimensional moduli space of disks that look like this, to compactify it, you exactly need to allow some bunch of the boundary points to come together and bubble off something like that, which exactly corresponds to some elements, some of your morphisms being composed using mu and then inserted into mu a second time. Is that okay, or should I expand a bit on that? Okay. So in particular, the Donaldson-Fukaya category is the cohomological category of the Fukaya category of M. Okay, and I've only got like 2 minutes, so maybe I can just say how one deals with the fact that in this definition, L0 and L1 are not always transverse to each other. So the way is basically, well, one way is for each pair of objects, L0 and L1, choose a Hamiltonian whose flow makes them transverse to each other. Then you can perfectly well define the differential mu1. When you come to define mu2, so mu2 should count things that look like this. And now here, rather than just having a J holomorphic curve equation asymptotic to some intersection, transverse intersection between two Lagrangians, we have this is not an intersection point, it's an intersection point of L0 with Hamiltonian flow of L1. And what one has to do is change the J holomorphic curve equation that you're looking at near these points so that the natural kind of asymptotic condition at those points is exactly a Hamiltonian flow line between your Lagrangians rather than an intersection point between them. And then you have to interpolate these alterations to the J holomorphic curve equation over the interior here. And you choose a way of doing that. You extend it to changing the J holomorphic curve equation in the neighborhood of all these guys in a way that's consistent with the way that the moduli spaces are supposed to degenerate, and you get some completely well-defined A infinity category, which, however, depends on some very large number of choices. Nevertheless, you can show that the final category you end up with is independent of all those choices up to the correct notion of equivalence of A infinity categories. No, which I haven't told you, but which I certainly will, because we want to end up comparing this with a B model, well, the derived category of coherent sheaves. And we want that comparison to be an A infinity comparison, not just comparison of categories. Okay, I think that's the end. That's 5. So.